Hello, my name is Bob D. Hilster and I am your particle model guru. Today's video is about the battery, and in particular we're going to talk about the wet cell battery. My last video was about the water and the universal solvent, and the main reason I did that one first of the series of 4 videos I'm making is because it helped understand what happens when you make an electrolyte. Because electrolytes are used in batteries, they're used in electrolysis, and they're used in cold fusion. So it's important to understand that there's a chemical reaction going on as soon as you make an electrolyte, even before you've made the complete battery. So here you have an example of a wet cell battery made with a copper electrode and a zinc electrode. The electrolyte for the zinc is made with zinc sulfate that's dissolved in water, and it immediately you release the zinc ion, sulfate ion, and you get the same thing with copper. Put copper sulfate in water, you get copper ion and sulfate ions. And that chemical reaction happens, as I just said, before you even put the zinc electrode or the copper electrode into their half cells. But in general, when you do, you get more chemical reactions. And so in general, what happens, we have electrons being released through the lamp over to the copper, and that causes the current flow through the electron flow, that is, through the light, and you have anion flow between the porous disk, which is separating the two electrolytes. That's generally what we have. Let's now talk about the electrodes. Copper and zinc are very common in batteries, but there are other metals, apparently other gases. Here's an interesting point, however. If you build a battery with 2 copper electrodes, there's no voltage developed. 2 zinc ones, 2 lead, doesn't matter. You make the battery out of 2 elements that are the same. There is no voltage, and that'll come up later in the discussion. The metals that do this are listed in what's called an electrochemical series. And this is an example here on the right of an electrochemical series, and you have fluorine gas at the top, and you have lithium at the bottom, and copper is here, and zinc is here. What's interesting to note about this list is that the voltage rating for these metals when they're put, each metal individually is put into an electrolyte, they have a voltage rating, and that voltage rating is biased around, not biased, but centered, if you will, around hydrogen gas, or the hydrogen ion. And that has a 0 volt value. So when you put copper into its electrolyte, it gives you 0.34 volts automatically, just by the chemical reactions. You put zinc into its electrolyte, and you get a negative 0.76 volts. So you can pick any 2 elements, and you can get a plus this and a minus that, and the sum of the two, or actually the difference of the two, gives you the voltage. If I use a silver in one and copper in the other, I'm going to get the difference between 0.8 volts and 0.34 volts, which is a half a volt. So in the case of the copper and the zinc, the copper gives you plus 0.34 and the zinc gives you a negative 0.76, but when you take the difference of that, you get a 1.1 volt battery. Happens automatically. You build the electrolyte, it has its chemical action going, you put the electrodes in, and you get whatever voltage you have based on what metals you're using. If you put 2 copper ones in there, you're going to subtract 0.34 from 3.4 and you get 0. Mathematically, that works. We'll see how that happens later. And generally, this is called a galvanic cell, named after a gentleman many years ago named Galvin. I found this link to a video, and well, a link to a paper and a video. It's kind of interesting. You got a neat explanation, and I recommend that you might want to get a different opinion of how things work, at least from a standard explanation. I recommend this link. From that link, I have this picture, and so now I'm going to talk about the chemistry, the total chemistry going on in order to generate this 1.1 volts. It all starts over here with the zinc and a chemical reaction down here where when the zinc is placed into the zinc electrolyte, it says 2 electrons are given, and an equivalent and 1 zinc ion having lost 2 electrons. And that releases 2 electrons, which obviously by the arrow they say move up through here, come back around down to here, and then when those 2 electrons reach the copper, you get this chemical reaction, and that describes the fact that these 2 electrons combine with copper, making copper atoms. It's an interesting point because copper does tend to accumulate over in this half of the cell. Presumably, my opinion is that the copper sulfate that's in solution combines with these electrons, and you get copper atoms, which is more than the copper electrode that's sitting there. Okay, so that's the electron flow, and then they have this salt bridge, and they claim that the zinc ion comes up and around. Here they call it sodium. I don't know if it looks like a typo here, so to speak. Comes over this way. The sulfate ion comes this way, and when you read about it and understand what they're saying, they're saying that the electrical charge needs to be neutralized, and this is how that happens, and that helps out in the equations. And here at least they're showing that when you have this zinc reaction to start with, you also get 0.76 volts potential at this point, and when this reaction happens you get plus 0.34 volts. I'm not sure whether this shouldn't have been a minus. My chemical equation, my understanding of these types of equations is not that clear. In any case, the combination of the 0.76 negative on this side and the 0.34 positive on this side gives you the 1.4 volts. That's basically the chemistry. As you might understand, these things are really more these kind of simplified versions of the equation, because it seems to me there's much more going on. But what you note is that the top half of that picture, where the electron is flowing, you have electrical current, and in the bottom half you have chemical current. Kind of an interesting point, which is emphasized from this link, and I'm going to read this. Electron flow from the zinc to the copper wire gives you the electron flow. Electron flows from the zinc to the copper. To balance the charge, ions flow through the salt bridge. Positive ions go from the zinc side to the copper, and some negative ions, that is to say that some less than the positive ions, some negative ions go the other way. So you have an electrical current through the wire and a chemical current through the bridge. It's more likely you'll hear me say that the electrons go out of the negative side over through the light bulb or meter to the positive side, and then it flows through from one electrode to the other. Look, that's what you're likely to hear me say. Have not referred to the fact that there is a chemical current, but apparently that's one way to view the battery. Okay, so let's talk about EMF, which is the force that moves electrons, and an electric field, which is the force that you see between a positive and negative charge. Now, when I've done my circuit videos, I've talked about the battery being the source of an EMF voltage to supply electrons to the circuit. The battery has an EMF force that causes these to move. That's what the battery does. But here, the very first thing that happens, or at least in my mind that happens, is you get the chemical reaction from the zinc electrode and the electrolyte, and it releases, and this starts moving. Starts moving before you even have a voltage. Well, if it's the EMF force that causes electrons to move, what's causing this to move? I read about and understand, I don't get any explanation of that. Of course, I don't get any explanation about what EMF force is anyway. But somehow we have electrons moving here before we even have an EMF force of the battery. Or is there an EMF force down here? An open question for which I don't have an answer. Now, the electric field is often only referred to as in terms of a capacitor. And if you look at the capacitor that is charged up, plus on one plate and minus on the other plate, they often refer to that there's a force field from the plus to the minus that can cause a charged particle to move. Maybe that's more with electrostatics, but if you're going to say that, it ought to apply here. But if you think about that, that there's the electric field is pushing this way, but the electrons are going that way, it doesn't work for a battery. That concept doesn't work. It may work for individual charge, things that are charged plus and minus, like in electrostatics, but it doesn't work here. Kind of strange as to what's really going on. What causes this to move? And of course, I've mentioned this before, electrons in a conductor, and zinc is a conductor, copper is a conductor, the wire is a conductor. It all gets moved, and it's moving at a speed of 3.2 meters per second, approximately. Very slow. Whereas the electron, when it was a part of the zinc atom, was orbiting at a very high rate. I'll leave that idea open. Okay, so let's take a look at the particle model. So we're going to use a zinc copper battery again to get a 1.1 volt battery. And in the particle model, there is no positive or negative charge. So whatever charge takes place in the chemical reactions in the flow of electrons versus the chemical flow, not there. I've said over and over again, there's a magnetic field around the battery. It's a little bit erratic. It's not as nice and neat as a magnet, but in my opinion, it's there. And in the particle model, I've said this for all of the circuits time and again, we get more G1s leaving or exiting the zinc than enter the copper. More G1s leaving the negative terminal of the battery than enter the positive terminal. Now today I'm going to change the voltage rating of the G1, and that's just for convenience. Number one, it's a false number. It's not necessarily at all true. The 0.1 volt per G1 that I used to use is just that's an assignment that is wrong, and so is this. But by choosing this, I can take the zinc voltage and I can make the correlation that if each G1 has 0.01 volts, that if you divide 0.01 into the 0.76, you can correlate that to the fact that there is 76 G1s being generated by the zinc electrode. And there are 34 G1s being generated by the copper electrode. So I'm going to use those numbers to talk about the circuit. So here's the model for the particle model battery. And as I've said over and over again, there is a G2 force field around all objects, including around the battery. Of course, there's a G1 force field around, but that isn't playing a major role here. And so you have G1 particles coming in and around and doing its thing. It's doing a lot. If you remember, the G2 force field is the nuclear binding force holding the copper electrode together, holding the zinc electrode, holding the ions together, holding the water together, it's doing a lot. It's a very busy force field. And when I've talked about the battery, as I said, there are G1 particles, and the red arrows indicate the G1 particles coming out of the negative terminal, going around and coming around. This is the way I would describe it. So how does that happen? Well, the first thing I want to understand is the direction. Why, it starts with zinc. The chemical reaction starts with zinc releasing G1s. And the question is, why do they go this way? Why this way, not down? So what you do is you look at that G2 force field, and in particular, you got forces in all directions, but looking at the G2 particles coming this way, G2 particles coming this way, and as they pass through the wire and the electrode, you have scattering. Some are scattered and trapped, some are scattered this way and trapped, and although there's a bit of an imbalance, there's not enough of an imbalance to tell me which direction the G1s are going to go. When you have the chemical reaction and the G1 particle is an orbital moving at a very high speed, when there's this mechanical reaction, remember the atoms are vibrating, and when they hit, they release, and these scatter all directions, and you don't know which way they're going to go. So how come they go this way? Doesn't appear to be this force here, and neither over here. This is got the same dynamics. G2 particles coming here, being scattered or trapped, and coming here, and I suspect in the center of the copper electrode and the zinc electrode, the forces are equal and opposite. So some of them should go down, some of them should go up, because the particles are there, and when they interact, they push. And so there's a continual up and down, even some left and right. Now there is a difference, though, between the copper electrolyte that's got this chemical reaction here and a reaction here, and that is the fact that there are, for each chemical reaction, there's 76 G1 particles for being released in this cell, half cell. Only 34 are being released here. So I get the feeling that there's more G1 particles here than there are here. In that case, the horizontal G2 force does have an imbalance. And you know, the G2 particle comes through here. There's a loss here, but it's not as big as the loss from here to here. So with a larger loss from here to here, you have a greater force pushing to the right. With a smaller loss from here to here, you have a lesser force pushing to the left. Again, they push both ways, but there's more G1 particles pushing this way than pushing left. It's the same with G1 gravity. I'm sitting here and G1 particles are pushing down on me, and some are pushing up, but there's more pushing down on me than pushing me up. And then that result is I feel a net force holding me down. So there's a net force going here, which might explain why these at least are going to the right, or at least there's a net flow of these going to the right. By the way, this chemical reaction takes place all around the copper electrode and the zinc electrode, so it's not just here. They could be moving across up here, or in the middle, or down here. Nonetheless, they do that. Making the turn is not odd. It's not unusual to make a right-hand turn here, or it's a left-hand turn here, because we see often that electrons flowing through a copper wire or a track on a circuit board makes a left-hand turn and goes there. So it makes the left-hand turn at these within the copper wire. So it can do that, but it's probably assisted by the fact that there's a magnetic field around this electrode and this electrode. Which way that magnetic field goes is still part of this up and down business, which isn't determined. This battery has got to find this configuration somehow. Even when you don't, even though you don't concern yourself with what's going on in the battery, I've said any number of times it takes several cycles for a circuit to find the right number of G1s that are needed to flow through the circuit to get a proper balance of voltages. Well, the battery apparently has to do the same thing. It's got to find its way. The one main thing that's happening is this way. Once this gets established and it enters here, somehow these going this way will be conducted in the copper wires. Some of them are going to go down, some of them are going to go up, and eventually it's got to establish this kind of path. And if you sense I'm having trouble trying to make this work, you're right. This is not like a magnet. A magnet is simple, straightforward, makes a nice magnetic field, and everything's well behaved and easily explained. Not so with the battery. It's difficult. You can see that that there are the possibilities there. But for me to give you a precise explanation of what's going on in here and why it does this is difficult. Because I'm saying there's a G1 particle flow across from here to here, and of course the standard model says no, electrons go from here to here and stop. And ion flow goes this way and stops. You got electron flow and you got ion flow, current. I'm saying no, it's G1 particles all the way around. Okay, one more thing about the numbers here. Assuming everything is now stabilized and working, You got every chemical reaction gives you 76 G1 particles, and this one gives you 34, but should really start over here where I start with 0. I'm assuming at this point when it's stable, I got 0 coming out of here. This generates 0.34 G1s, this adds 0.76, and you get 110 G1 particles, which is exactly what you need to get a 1.1 volt drop across the shunt resistor that's inside that meter. But of course, that's not quite enough. The interaction factor and the volts per G1 is a factor in determining how many you really need going around and around and around. That's the G1 base I've talked about. But you can see how plus 34 and plus 76, even if there's 10,000 coming in here, you got 10,000 plus 34, 10,000 plus 76, 10,000 plus 110. 110 are lost, giving a voltage drop, and I got 10,000 back. I got a balanced circuit. The battery has to determine how this flow is going to be and get there, and the circuit has to determine what the G1 base is. It all takes time. Remember earlier I said if you use copper in both sides of the battery, you don't get a voltage. This is one of the ones that seem to work out a little bit better, because the copper one here going to generate plus 34, and this is going to generate plus 34, and it's going to give me 68 G1 particles out of the negative side, and that's going to give me 0.68 volts through the voltmeter. That's not right. That's not the way it works. There has to be something else going on. They say that when you do that, you don't get a voltage across. This reads 0. So what's happening? Well, if this is copper and that's copper, the G1 particle density here and the G1 particle density here is the same. And therefore, there is no net force to the right pushing them this way. There's no way to establish that flow. They don't know which way to go. If you don't get a net flow, if half of them are going left and half of them are going right, you're never going to get any net flow this way that's going to give you a voltage. So, this is what I think helps get the 1.1 volt established when you have copper and zinc. When you have copper and copper, it kind of halts that whole process. So, the particle model. Oops, I went backwards. Come on, Robert. Here we go. In conclusion, the standard model, I would question what's moving the electron in the first place. They have no explanation. Not even their idea that there's an EMF doing it that even doesn't come into play. They don't explain the direction. And they talk about the fact that there's an electrical current and a chemical current flow. Electrical through the wire, chemical through the electrolyte. The particle model, however, maintained the G1 is already moving at high speed. The zinc terminal releases more G1s than more G1s, and the copper terminal accepts them. The G2 force field is the only thing that can control the direction. The G2 particle and a force field has always been what controls the flow of G1s. In refraction, when I first brought that up, it was the G2 particle that causes the light to bend. If it can cause a light to bend there, it can cause it to turn corners and move in different directions inside the battery. G2 force field turns the G1s in. It helps. It's not only the direction, but it's the turns that are happening by the G2 force field. Yeah, this is a little bit harder to explain. Number one, the standard explanation isn't exactly clear. It's hard to establish exactly what the pattern of G2 force is because of the irregularity of the model. So it's difficult. Some of these things I just recently learned myself. I'm trying to understand it. This whole subject of a particle model being mechanical and the chemical chemical reactions being mechanical. This is all new. I've been working on it 3 years, but it takes time to work on each one of these things. And as I get into more detail of each of these things that we're going to talk about in the future, it's going to get harder and harder to make it work exactly. The question I'm left with, is there enough there to say, okay, maybe with some experimentation, maybe with more analysis, more study, whatever I can do, I can get a more clear answer. I think the possibilities are there. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.